M1 Abrams, the birth of America's main battle tank. But the story of the Abrams begins with a problem the United States could not afford to ignore. By the late 1970s, the United States found itself in an uncomfortable position, one that was almost unthinkable for a superpower. And the consequences of that gap could have been catastrophic. A country with the world's largest economy and enormous defense spending suddenly realized that its tank forces had fallen significantly behind their primary adversary. While Soviet engineers were introducing new armored vehicles one after another, American tank crews were still operating machines that had been designed during the Eisenhower administration. In a Cold War battlefield, that kind of technological lag could decide the outcome of an entire war. And this was not just a technical issue. It was a genuine strategic problem that could have cost the United States dearly in the event of a large-scale war in Europe. At that time, the backbone of the U.S. Army's armored forces was the M60 tank, which had entered service back in 1959. The vehicle had been respectable in its day, but that day had long passed. Over 2 decades of service, the tank underwent several upgrades, the last of which, the M60A3, began entering service in 1978. Yet none of these improvements addressed the core issue. At its heart, the vehicle was still a design from 20 years earlier, with outdated armor, an aging gun, and only average mobility. Meanwhile, on the other side of the Iron Curtain, events were unfolding very differently. The Soviet Union was steadily introducing new generations of armored vehicles. First came the T-62, equipped with a smoothbore gun. Then the revolutionary T-64, featuring an automatic loader. And finally the T-72, a mass-produced tank that began entering service by the thousands. And the numbers behind these tanks were even more alarming. Each of these vehicles surpassed the American M60 in one way or another, and Soviet industry was producing them in enormous numbers. For the Pentagon, the message was clear: the balance of power was shifting. What made the situation even more frustrating was that the United States could have had a modern tank of its own. The United States had already tried to solve this problem once. During the 1960s, American engineers had been working together with West Germany on an ambitious project known as the MBT-70. The vehicle was intended to be a major breakthrough in tank design. Engineers planned to equip it with a 152mm gun capable not only of firing conventional shells, but also of launching guided anti-tank missiles through the barrel. On paper, the MBT-70 looked like the most advanced tank ever conceived. Nothing like this existed anywhere else in the world, and American and German planners expected it to provide overwhelming superiority over any potential opponent. But the ambitious project gradually turned into a nightmare for the defense budget. And the deeper engineers went into the project, the worse the problems became. Development costs kept rising year after year, while technical problems multiplied faster than engineers could solve them. By the early 1970s, it had become clear that bringing the tank into production within a reasonable time frame was no longer realistic. At the same time, the United States was facing economic pressure. The Vietnam War was consuming billions of dollars, inflation was rising, and members of Congress were becoming increasingly reluctant to approve expensive military programs. In 1970, the Pentagon made the difficult decision to cancel the MBT-70 program. Billions of dollars spent on development were effectively written off. It was one of the most expensive failures in the history of American armor development. American engineers attempted to salvage something from the project and continued working on a simplified version of the tank, designated XM803. However, this vehicle also proved to be too complex and too expensive. And when that project failed as well, the U.S. Army was left almost exactly where it had started. By the end of 1971, that program was canceled as well, effectively ending hopes for a rapid modernization of the Army's tank fleet. The U.S. Army gained very little from the entire effort. The 152mm gun that had been central to the project did see limited use. It was installed on the aging M60, creating the M60A2 variant. However, this version proved so problematic that only 526 units were produced, compared to more than 15,000 M60 tanks overall. Another vehicle that used the same weapon system was the M551 Sheridan, a light amphibious tank designed for airborne forces. About 1,700 of these were built, and they even saw combat in Vietnam, but the Sheridan was never intended to replace a main battle tank. By this point, the situation had become critical. Soviet armored formations in Eastern Europe numbered tens of thousands of modern tanks, while the United States could oppose them only with the aging M60. In the event of a large-scale war, these tanks would have been tasked with stopping a Soviet advance across West Germany, and Pentagon planners understood very well how that might end. Something had to be done. The Pentagon needed a completely new approach. In February 1972, the chairman of the Joint Chiefs of Staff, Admiral Thomas Moore, announced a competition to develop a new main battle tank. American tank development was being given one last opportunity to prove that it could still produce a world-class armored vehicle. 3 of America's largest industrial corporations submitted proposals for the competition, each with extensive experience working on military contracts. These companies were Ford Motor Company, General Motors, and Chrysler, and each company believed it had the answer to America's tank problem. The competition promised to be intense. At stake was a contract worth billions of dollars, along with the prestige that would come with building the U.S. Army's next generation of armored vehicles. Ford Motor Company chose the simplest and most practical approach. Its engineers proposed not reinventing the wheel, but instead using the West German Leopard 2, which at that time was undergoing trials and showing excellent results, as the foundation for the new tank. The Germans had produced an outstanding design, and Ford engineers suggested adapting it to American requirements. The primary challenge would have been converting the entire technical documentation from the metric system to the imperial system, which was traditionally used by American industry. On the surface, the idea seemed reasonable. Why spend years developing a new vehicle if an ally had already done most of the work? General Motors chose a very different strategy. The company decided not to abandon the work done under the failed MBT-70 program and proposed to continue developing the simplified XM803, which had been canceled only a few months before the competition was announced. Engineers at General Motors believed they could refine the design and eliminate the issues that had doomed the original project. In essence, they were asking for a second chance and promised that this time the project would succeed. The third participant, Chrysler, submitted a proposal that initially appeared to be the riskiest of the 3. Instead of relying on proven solutions, Chrysler's engineers proposed building an entirely new vehicle centered around a revolutionary power plant. That decision would ultimately shape the future of American tank design. At the heart of Chrysler's tank would be the AGT 1500 gas turbine engine, developed by the company Lycoming. The history of this engine dated back to 1964, when Lycoming began developing it in the hope that it would power the ill-fated MBT-70. However, the designers of the German-American tank had ultimately rejected the gas turbine in favor of a more traditional diesel engine produced by Continental. Now the turbine was being given a second chance. The gas turbine engine offered several clear advantages. It produced 1,500 horsepower, making it one of the most powerful tank engines in the world. At the same time, the turbine was remarkably flexible in terms of fuel. It could run on gasoline, diesel fuel, aviation kerosene, and even heavy fuel oil. For an army expected to operate in many different regions of the world, this kind of flexibility was highly valuable. However, gas turbines also had serious drawbacks, and critics of the project frequently pointed them out. The most significant was extremely high fuel consumption, which on average was roughly twice that of a conventional diesel engine. For a country that had just experienced the 1973 oil crisis, this was a major concern. There was also another unexpected issue. The gas turbine turned out to be surprisingly heavy. With a mass of 3,850 kilograms, it weighed nearly twice as much as the Continental diesel, which produced only about 25 horsepower, less yet weighed just 2,080 kilograms. The unusual design decisions did not end there. A gas turbine engine does not necessarily require a conventional gearbox, unless it is a single-shaft design. A turbine can naturally vary torque across a wide range of rotational speeds. Nevertheless, Chrysler's engineers equipped their tank with a hydromechanical transmission with a torque converter, which consumed roughly 10% of the engine's power. Why this additional component was included was not entirely clear, but the military accepted the solution without significant objections. Evaluating the competing proposals took several years. Military planners carefully studied each concept, weighing the advantages and disadvantages. Ford's proposal was rejected largely for reasons of national pride. The U.S. Army was not prepared to field what was essentially a German tank, even if it had been modified for American standards. The proposal from General Motors was also rejected for fairly obvious reasons. Few were willing to invest further resources in a design that had already failed twice. On November 12, 1976, the Pentagon finally announced the winner of the competition. The contract went to Chrysler with its gas turbine-powered tank. Despite the drawbacks of the proposed power plant, military planners concluded that its advantages outweighed its disadvantages. Power, multi-fuel capability, and the relative mechanical simplicity of the turbine ultimately won the debate against the greater efficiency of diesel engines. The United States had chosen a bold technological path. Now the challenge was to turn the design into a real combat vehicle. The new tank was named in honor of General Creighton Abrams, who had commanded U.S. forces in Vietnam and later served as Chief of Staff of the U.S. Army until his death in 1974. Years of intensive engineering work still lay ahead before the tank could enter full-scale production. Winning the competition was only the beginning of a long and demanding journey. Now Chrysler's engineers faced a challenge that tank designers around the world had been struggling with. How could a tank be protected from modern anti-tank weapons that were becoming more lethal every year? Shape-charged munitions could burn through conventional steel armor as if it were paper, while new kinetic penetrators were capable of punching through thicknesses of metal that had only recently been considered completely reliable protection. A fundamentally new solution was required. The answer came from across the Atlantic in the small English town of Chobham, located in the county of Surrey. It was there, at a research facility operated by the British Ministry of Defense, that scientists developed a revolutionary type of armor that would later become known by the name of the town itself. This armor was a highly complex, multi-layered structure, combining different materials in such a way that it could counter multiple types of threats. American engineers quickly realized that this British development was exactly what their new tank needed. An agreement was signed between the two countries to transfer the technology, and a group of Chrysler engineers traveled to the United Kingdom for extended training. There, in the town of Chobham itself, they studied the manufacturing techniques behind this unusual armor, technology that would later protect American tank crews on future battlefields. The structure of the new armor was remarkably complex. The cheek armor modules, protecting the most vulnerable parts of the turret, consisted of large composite structures made up of numerous layers. At the front was a rolled homogeneous steel plate measuring 63.5 millimeters in thickness, installed at an angle of 55 degrees from the vertical. Behind it was an empty cavity more than half a meter wide, followed by a rear armor plate 101.6 millimeters thick. But the real secret of the protection lay within that cavity. Inside were packages of composite metal ceramic plates, each 19 millimeters thick, separated by 4 millimeters layers of natural rubber. The ceramic mixture included aluminum oxide, aluminum nitride, barium titanate, and even corundum, a material second only to diamond in hardness. When struck by a projectile, the ceramic fractured and absorbed enormous amounts of energy while spreading the impact over a larger surface area. Between the composite modules and the rear armor plate was another protective element known by the abbreviation NARA, which stands for Non-Explosive Reactive Armor. This structure consisted of alternating 15 millimeters aluminum plates and 7 millimeters steel plates, separated by 4 millimeters rubber layers. When struck by a shape-charged jet, these layers shifted relative to each other, disrupting the formation of the jet and significantly reducing its penetrating power. The lower front hull plate had a similar internal structure, although it contained fewer composite layers. The front plate in that section was thinner, only 31.75 millimeters. The turret sides also received multi-layer protection, though the outer armor plate there was even thinner, measuring 30.48 millimeters. The upper glassy plate, however, whose thickness had long been the subject of speculation, turned out to be surprisingly thin. Various publications had claimed values of 76 millimeters, 80 millimeters, or even 125 millimeters, but the actual thickness was only 38.1 millimeters. What protected this section was the extremely steep angle of the armor, 82.5 degrees from the vertical. At such an angle, the fuses of many anti-tank guided missiles failed to activate properly, while kinetic penetrators either ricocheted or were forced to travel through the equivalent of nearly 300 millimeters of steel due to the angle of impact. At the same time that armor protection was being finalized, another major debate was taking place. What gun should be installed on the new tank? The designers originally proposed using the 120 millimeters smoothbore gun produced by Rheinmetall, the same weapon installed on the Leopard 2. However, the U.S. military unexpectedly opposed this idea. Tank crews insisted that the first production Abrams tanks should be equipped with the older 105 millimeters rifled M68 gun, which was a licensed version of the British L7 and had already been installed on all versions of the M60. The main argument in favor of the smaller caliber was the larger ammunition load, 55 rounds instead of 40. In addition, by the time Abrams entered production, new armor-piercing, fin-stabilized, discarding sabot rounds had already been developed for this gun. These rounds had first been introduced with the M60A3. American planners expected to compensate for the smaller gun's lower power with greater accuracy, thanks to the Abrams modern fire control system. Soviet tanks relied on automatic loaders, which allowed for a higher rate of fire. But American commanders believed their crews would be able to destroy enemy tanks with the first shot, leaving no opportunity for the opponent to respond. On February 25, 1980, at the tank plant in Lima, Ohio, an event took place that the U.S. Army had been waiting for nearly 10 years. The first production M1 Abrams rolled off the assembly line. A machine that had traveled a long path from design drawings to steel had finally taken physical form. American tank development was entering a new era, and now it had to prove that all the years of work and the billions of dollars invested had not been wasted. The first production M1 Abrams tanks were equipped with a 105 millimeters M68 gun, the weapon the military had insisted on using. However, the ammunition for it was no longer the same as that used by the older M60 tanks. By the time production began, an improved version of the M735 armor-piercing, fin-stabilized, discarding sabot round had already been developed. This new round was designated M735A1. The key difference in the new projectile was the material used for the penetrator. Instead of tungsten, it used depleted uranium, with a purity of about 99.4%. Depleted uranium was a byproduct of uranium enrichment for nuclear power plants and nuclear weapons. The United States had accumulated enormous quantities of this material, and the military found a very practical use for it. The density of depleted uranium is significantly higher than that of tungsten, giving the projectile exceptional armor-penetrating capability. In addition, a uranium penetrator has a unique property known as self-sharpening. When penetrating armor, it does not flatten like tungsten, but instead maintains a sharp tip, which further increases its effectiveness. However, uranium ammunition also had a drawback that was rarely discussed openly. Depleted uranium is weakly radioactive, and prolonged exposure to it can pose certain health risks. For this reason, the Abrams ammunition load was stored in a special compartment in the turret bustle, separated from the crew by an armored partition. Officially, this partition was intended to protect the crew from a catastrophic ammunition explosion. At the same time, it also served as a form of shielding, protecting the crew from the small but continuous radiation emitted by the uranium rounds. As production of the Abrams increased, it soon became clear that the tank would require further improvements. In August 1984, after 2,374 tanks of the base model had been produced, the upgraded M1A1 variant entered service. This version finally received the 120mm rainmetal smoothbore gun that the designers had originally proposed. American military planners had concluded that accuracy alone was not enough, and they agreed to adopt the more powerful gun, even though it reduced the ammunition load to 40 rounds. In addition to the new weapon, the M1A1 received a collective protection system against weapons of mass destruction. This allowed the tank to operate in environments contaminated by nuclear, chemical, or biological agents without exposing the crew to lethal danger. Another addition was an air conditioning system, which in hot climates was not a luxury, but a necessity for maintaining the crew's combat effectiveness. All of these improvements inevitably increased the tank's weight. The original Abrams weighed 54 tons, while the M1A1 increased to 57 tons. The additional 3 tons required modifications to the suspension and the development of new tracks capable of handling the increased load. At the same time, boron carbide was introduced into the composite armor, increasing its hardness, but also significantly raising production costs. Interestingly, production of 105mm Abrams tanks continued alongside the M1A1. These vehicles remained in production until May 1986 in an upgraded version known as Improved Performance. They received all of the improvements introduced on the M1A1, including nuclear biological chemical protection and air conditioning, except for the new gun. A total of 894 tanks were produced in this configuration. The introduction of the NBC protection system led to an unexpected problem. The equipment occupied part of the tank's internal space, leaving the crew with very little room to store personal gear. Engineers were concerned that tank crews might start placing their equipment on the roof of the turret bustle, where the blow-off panels were located. These panels were designed to be forced outward during an ammunition explosion, directing the blast away from the crew and giving them a chance to survive. Any additional weight on the panels could interfere with their function and potentially cost the crew their lives. The solution was simple and effective. A storage rack was welded to the rear of the turret. This became the most visible external feature, distinguishing the improved M1 tanks from earlier production vehicles. A similar rack was also installed on the M1A1, though it was slightly larger. In 1988, American engineers took another step in improving the protection of their main battle tank. Until then, depleted uranium had been used only in ammunition. Now it was introduced into the armor itself. The idea was simple and elegant. The same material that was so effective at penetrating enemy armor could also be highly effective at resisting enemy projectiles. The new armor was a further development of the Chobham composite armor concept. Inside the composite armor modules, an additional layer of depleted uranium was inserted. These uranium plates were clad in graphite to prevent corrosion and reduce radiation levels. Because the United States possessed large reserves of depleted uranium as a byproduct of nuclear industry, the military could afford to implement this expensive solution. However, not all tanks received the new armor. Vehicles equipped with the enhanced protection were designated M1A1HA, where the letters HA stood for heavy armor. These tanks were intended for units expected to operate in the most dangerous sectors, where the likelihood of encountering modern enemy armored vehicles was highest. A new 120mm round, the M829, was developed for the M1A1's gun. This projectile used a solid, depleted uranium penetrator. For the first time in the history of American tank design, the armor penetration of a U.S. tank round surpassed that of contemporary Soviet ammunition. American tank crews now had a weapon capable of defeating virtually any armored vehicle at ranges previously considered impractical. By the early 1990s, the U.S. Army fielded an entire family of vehicles based on the Abrams platform. The original M1 with the 105mm gun. The improved M1 improved performance, equipped with the same gun but with NBC protection. The M1A1, armed with a 120mm gun. And finally, the M1A1HA, fitted with depleted uranium armor. Each of these variants had its own characteristics, strengths, and limitations. But all of them represented a major leap forward compared with the aging M60. A total of 2,374 tanks were produced in the original M1 configuration. Another 894 improved M1 tanks were built with NBC protection. The M1A1 was produced in even larger numbers, with some receiving uranium armor directly at the factory and others upgraded later. American industry was operating at full capacity, supplying the Army with its new generation of armored vehicles. 10 years had passed since the first production Abrams left the factory in Lima, Ohio. During that time, the tank had evolved from an experimental vehicle with an unproven gas turbine engine into the backbone of the armored forces of the world's most powerful military. Engineers had solved early technical problems, the military had refined its tactics, and industry had established large-scale production of spare parts and ammunition. Throughout this period, Abrams tanks served in Western Europe, preparing for a war that fortunately never came. Soviet armored formations still stood on the other side of the Iron Curtain, but the balance of power no longer appeared as threatening. American tank crews had confidence in their machines and were waiting for the opportunity to test them in real combat. That opportunity came in August 1990, when Iraqi forces invaded Kuwait. The tank would soon face its first real war. The United States immediately began deploying forces to the Persian Gulf, and along with infantry and aircraft, American tanks were sent as well. For the first time, all 4 Abrams variants then in service were brought together in one theater, ready to face an army equipped largely with Soviet-designed vehicles. In January 1991, the operation to liberate Kuwait began. The Abrams would soon face Iraqi T-55, T-62, and T-72 tanks, the very vehicles whose superiority American engineers had spent years trying to overcome. And that superiority had finally been achieved. During the fighting, Abrams crews destroyed hundreds of Iraqi tanks without suffering a single direct combat loss. An extraordinary result. The battlefield had delivered its verdict. The U.S. Army had received a truly remarkable machine, one that is widely regarded as one of the best tanks ever built. And decades later, the Abrams still remains one of the most powerful main battle tanks ever deployed.